Good day, I'm Alana Corinne Wee, and I'll be here to give you an overview about the standard penetration test. Now, the standard penetration test is used to identify three things. First is the soil type, second is the stratigraphy, and third is it's a relative measure of strength. The SPT was developed in the United States around 1927. And the SPT was originally developed for sand, but nowadays it can be used for all types of soil at a given depth. It is a well-established method of investigating soil properties such as bearing capacity and liquefaction. It is also the most popular and economical means of obtaining subsurface information. As stated in Bowles, 1997, 85 to 90% of conventional foundation designs in both North and South America is made using SPT. The method was standardized in 1958 as ASTM-D 1586. This test consists of mainly three things. First is driving the standard split barrel sampler of dimensions a distance of 460 mm into the soil at the bottom of the boring. Second is counting the number of blows to drive the sampler the last to 150 mm distance, a total of 300 mm, to obtain the N number. Third is using the 63.5 kilogram driving mass or hammer falling free from a height of 760 mm. Several hammer configurations are available. Before we proceed to how the test is actually done, let's look at some equipments in it and their specifications. First, we have the drilling rig. Second is the split spoon. Third is the drop hammer. Next is the driving head. Next is the guiding rod. Then we have the tripod. Then we have the extension rods. Moving on to the procedure, first we have to erect the tripod over the test hole and assemble the unit. Second, allow the spoon to rest on the bottom of the hole. Third, drive the spoon with the blows from the hammer falling 75 centimeters until either 45 centimeters have been penetrated or 100 blows have been applied. Fourth, record the number of blows required to affect each 15 cm of penetration. The first 6 inches is considered a seeding drive. Next, the number of blows required for the second and third 15 cm of drive added is recorded as the penetration resistance value, or N, of the soil. The SPT values are presented either in the form of a table or in the form of a bore log data. This is the image of a standard dimensions for the SPT sampler. The boring log shows refusal and the test is halted if first, 50 blows are required for any 150 mm increment. Second, 100 blows are obtained to drive the required 300 mm. Then lastly, 10 successive blows produce no advance. When the full test depth cannot be obtained, the boring log shows a data of 70 over 100 or 50 over 100, indicating that 50 or 70 blows resulted from the penetration of 100 mm. Now this is the cost per foot of SPT. From 0 to 50 feet, it would cost 595 pesos and 91 cents. 51 to 100 feet would cost 704 pesos and 26 cents. 101 to 150 feet would cost 920 pesos and 96 cents. Now that is all for this discussion, and let us move on to the SPT correlations.
So good morning everyone, my name is Jomel J. Abina and today we'll be discussing the standard penetration test correlations. In standard penetration test correlations, we correlate the standard blow number with the other variables. So before that, let's discuss about the energy related in standard penetration test. So the energy input in the standard penetration test is equal to the weight times height. So according to Kovacs and Salomon in 1982, they found out that the actual input driving energy, which is represented by E sub A, to the sampler to produce penetration ranged from about 30 to 80%, while according to Riggs, EA ranged from about 70 to 100%. So these discrepancies between energy in and EA are because of either equipment from different manufacturers, drive hammer configuration, overburden pressure, and length of drill rod, and other factors. So in order to um, correct these discrepancies, the SPT energy is standardized to the represented by an energy ratio, which is ER is equal to EA over EN times 100. So next is in order to correlate this SPT test and standard penetration test, the other variables, we need to talk about the standard blow count. So the standard blow count is N70. It has been standardized that since recent data using current drilling equipment show that N70 is close to the actual energy ratio obtained in North American practice. So N70 is equal to C sub n times eta 1, 2, 3, and 4. So where Cn is the adjustment for effective overburden pressure as seen here, and eta I is adjustment factors from and computed as shown in table 3-3. So in order to compute for Cn, it is given here that it is equal to 95.76 over PO raised to 1 half. So this is table 3-3 found in page 159 of Foundation Analysis and Design 5th edition by Joseph E. Bowles. So now we are ready to correlate SPT and 70 to other variables. So first we will talk about the angle of internal friction. So the angle of internal friction is equal to square root of 18 times N70 plus 15. The second one is equal to 0.36 times N70 plus 27. And the third one is 4.5 times N70 plus 20. So the third one is commonly used in general, while the first is used commonly for roads and bridges, and the second one is used for buildings. Now, the second variable to be talked about is the relative density. According to Meyerhoff, 1957, his formula is N over dr squared is equal to A plus B multiplied by PO, where PO is the in situ overburden stress and it is equal to the summation of unit weight times Z. So, therefore, the unit weight could also be correlated to N, the number of blows. And A and B are site-dependent variables, whereas dr is relative density. So Skempton also proposed another formula in 1986. It is N70 over dr squared is equal to 32 plus 0.288 multiplied by the in situ overburden pressure. He also had proposed another formula, but this time for the over-consolidated soils. So as shown here, it is N70 over dr squared is equal to A plus B multiplied by the coefficient of over-consolidated soils multiplied by in situ overburden stress. So to define the coefficient of over-consolidated soils, first is let the mean effective normal stress be defined as the summation of stresses in the XYZ over 3. So as defined in section 2 of Joseph E. Bowles' book, stress in X and Y is equal to KO multiplied by the stress in Z. Now on substitution to the above and using PO to substitute the variable for the stress in Z to obtain the mean effective normal stress in situ. This is for normally consolidated soils. So as seen here, the coefficient of over-consolidated soils multiplied by the in situ overburden stress is equal to 1 plus 2 multiplied by K over 3 multiplied by PO. So substituting this to the first formula and using the third step, which is defining the usage factor, COCR is equal to P of normally consolidated soil over the P of over consolidated soils. So therefore, we get this formula below. COCR is equal to 1 plus 2 K of normally consolidated soils over 1 plus 2 multiplied by K of overly consolidated soils. So the relationship between relative density and the angle of internal friction was shown by Meyerhoff in 1959 and is given by phi is equal to 28 plus 0.15 multiplied by dr. And lastly, for the last variable, we will correlate the number of blows with Q sub U. And the Q sub U is equal to Kn, where K is a constant, and the relationship of both can be found in table 3-5, page 163 of Joseph E. Bowles' book. So that's all. and on to the designing of n values.
So good morning, I am Daniel Leonard Wong and I'll be talking about designing end values, which is the third and the last part of this discussion on standard penetration test. In estimating end values, Terzaghi and Peck 1948 proposed that obtaining the smallest end value within the zone of major stressing, which is under the soil layer that is occupied by a footing, is already possible. So this is the old way of obtaining the smallest end value or the end value for a soil layer. So under a soil layer, depth parameters are imposed to locate where we select the end values. So for bowls, he says that depth parameters are must be within half of B above the footing to a depth of B below the footing. So for this case, if this is the footing with the width of B, end values needed are 1/2 of B above the base of the footing to a depth of 2B below the base of the footing. So all end values within this area are included or are considered for the averaging. Bowles also suggested the formula of weighted averaging using the depth increment to determine the n value for footings. So the n average is equal to the summation of the product of n multiplied by the depth for that layer, which is zi, all over the summation for zi, which is again the depth, where z is from the ground surface. So all n values are rounded off to the nearest whole number. So no n values will have a decimal place. So for pile foundations, a simple averaging of all n values within the depth parameter can be used. If the section is thick, he suggested, or both suggested, subdividing it into sections and obtain the average n values for each section. So this averaging is only applicable for pile foundations. Footing foundations or footings are not applicable by simple averaging. So for this case, if the footing is thick, or it can be subdivided into layers and then average the end values for each layer. So for correcting end values, Bowles said that the corrected end values can be obtained by correcting the average end values or averaging all the corrected end values. So again, to obtain corrected end values, you could average the end values for the entire soil layer first and then correct the end value. Or you could correct the end value for each soil layer and then average all the corrected end values. So to conclude this series on soil testing, for this case the standard penetration test, uh, this standard penetration test would be very beneficial in terms of initial assessment for soil foundations. And so this would be a good topic to discuss on soil analysis and the fundamentals of geotechnical engineering. So thank you, and I hope you have learned something from us.